Imagine that the journey is already over. After years in darkness, the spacecraft has crossed the distance between the Sun and Alpha Centauri. Ahead, another star fills the view. Behind the ship, our Sun has become a faint point of light, almost impossible to separate from the stars around it. Earth is somewhere beside that point, too small to see, but its position is still known. On a map, the next step looks simple. Turn the spacecraft around. Draw a second line beside the first. Follow it back to Earth. That apparent symmetry is comforting because journeys on Earth usually work that way. A road crossed in one direction can normally be crossed again. Yet interstellar travel is not a road, and arrival does not leave a vehicle unchanged, refueled, protected, or ready to repeat everything it has just survived. Nothing in known physics places an invisible wall across that return path. A spacecraft moving below the speed of light is not forbidden from traveling home. Alpha Centauri is not a trap with a door that closes after arrival. In principle, the route works in both directions. But a line on a map carries no fuel. It provides no energy. It does not slow the spacecraft when it reaches the destination, keep its passengers alive, repair damaged machinery, or prepare the vehicle to leave again. It does not show what happens to Earth while the travelers are away. The return arrow appears identical to the outward arrow only because the hardest parts of the mission have been hidden. To come back, the spacecraft must first arrive in a useful sense. Racing through the system at enormous speed would count as reaching Alpha Centauri, but not as stopping there. The vehicle would need some way to remove the motion it had spent so much energy gaining. Then it would need enough working equipment, stored resources, or local infrastructure to begin another interstellar journey in the opposite direction. Its passengers would have to survive every stage. Their habitat would need to protect them throughout the crossing. Air, water, food, power, medicine, and waste systems would have to keep working without quick rescue or replacement from Earth. The ship would need to endure the space between the stars once on the way out and again on the way home. Every protective layer, spare component, and reserve would add more mass, and every added piece of mass would have to be accelerated and stopped. Even success would leave another question. Returning to Earth does not automatically mean returning to the world that was left behind. The travelers in Earth may not experience the same amount of elapsed time. A spacecraft could arrive back at the correct planet while finding that the people, institutions, and shared present once called home had moved far beyond it. So the word never must be handled carefully. It does not mean that nature has written a law saying no traveler can trace a path to Alpha Centauri and then trace another path back. The stronger and more honest possibility is that the journey becomes irreversible in practice. The original travelers may be unable to complete it within their lives. A faster ship may demand energy and protection that no real vehicle can provide, and a journey that saves time for those on board may still carry them away from the time of Earth. That is the real investigation, not whether a return line can be drawn, but whether the same people can cross the distance, stop, survive, turn around, cross it again, and still call what waits for them home. Before any engine, shield, or clock can be tested, the distance itself must be understood. Alpha Centauri is often called our nearest neighboring star, as though nearness makes the journey familiar. But what exactly is waiting there, and what does 4¼ light-years demand from an actual spacecraft? The name Alpha Centauri sounds like the name of a single star. From Earth, that impression is easy to understand. To the unaided eye, the brightest part of the system appears as one point in the southern sky. Yet the destination hidden inside that point is not one place. It is a system of 3 stars, separated from one another by distances large enough to matter locally, even though all 3 seem almost equally remote from us. 2 of those stars, Alpha Centauri A and Alpha Centauri B, form a bright pair. They orbit a shared center, bound together as a binary system. The third star is Proxima Centauri, also called Alpha Centauri C. It is smaller, cooler, and much dimmer than the other 2. Proxima follows a far wider path around the pair, making the system less like 3 lamps standing together and more like a close partnership with a distant companion. Proxima is the nearest of the 3 to our solar system. Its name reflects that position. The distance from Earth is about 4¼ light-years. Alpha Centauri A and B are slightly farther away, at roughly 4⅓ light-years. That difference would matter to a spacecraft trying to reach a precise target, but it does not change the central scale of the journey. Whichever member is chosen, the vehicle must cross more than 4 light-years of interstellar space. A light-year is often misunderstood because its name contains the word year. It is not a measure of travel time. It is a measure of distance, the distance light covers during 1 year. Light moves so quickly that it can circle Earth many times in a single second. Yet even light needs more than 4 years to travel from Alpha Centauri to us. The system we see in the sky is therefore not shown as it is now. We see light that began its journey years ago. Across 4¼ light-years, the distance to Proxima is roughly 40 trillion kilometers. Writing the number does not make it easy to imagine. Human experience offers almost nothing on that scale. Journeys between cities, around Earth, or even to the Moon occupy only a tiny part of the gap. The distance from Earth to the Sun, which already feels enormous in ordinary terms, is only 1 astronomical unit. Scale that Earth-Sun distance down until it measures 1 meter. On this model, Earth would sit 1 meter from the Sun. The outer planets would occupy only a small area nearby. But Proxima Centauri would not stand across the room or at the end of the street. It would be roughly 268 kilometers away. Reducing the solar system to a walkable model still leaves the nearest star in another city. That distance is not an estimate produced by imagination. Astronomers can measure it through parallax. As Earth travels from one side of its orbit to the other, a nearby star appears to shift slightly against the much more distant background. The shift is extremely small, but it provides a geometric baseline. The smaller the apparent change, the farther away the star is. Modern observations refine that measurement with remarkable care, allowing astronomers to place Proxima and the brighter pair at slightly different distances. For generations, improving this measurement changed Alpha Centauri from a bright neighbor into a destination with known depth. The apparent point in the sky became a 3-dimensional system. That distinction is important for the journey. Navigation can identify where the spacecraft must go, but precision does not make the route shorter. Better maps remove uncertainty about the target, while leaving the physical separation untouched. In this case, knowledge sharpens the problem, instead of solving it for any future crew. The method matters because the problem begins with firm evidence. Alpha Centauri is not declared unreachable because its distance is vague or mysterious. The gulf is measurable. Its size can be translated into kilometers, into the time required by light, and into a scale model based on Earth's orbit. We know where the system is well enough to understand exactly why calling it nearby can mislead us. Nearby is always a relative word. Among stars, Alpha Centauri is our closest neighbor. Compared with the width of the Milky Way, it lies almost beside us. But a spacecraft does not cross a percentage of the galaxy. It crosses every kilometer between departure and arrival. The fact that no other stellar system is closer offers no engine, no protection, and no reduction in the distance itself. The three stars also prevent the destination from being treated as a simple dot. Reaching Proxima is not the same as reaching the bright binary. A mission would need a selected target, a planned approach, and eventually some way to control its motion inside that system. Those details will matter later. For now, the essential fact is simpler. The smallest available interstellar crossing is still about 40 trillion kilometers. That number establishes the distance, but not the duration. A gap can appear manageable or impossible depending on the speed used to cross it. Light completes the journey in a little more than 4 years. A human spacecraft cannot move at light speed. To understand what the same distance means for our machines, the next step is to stop thinking in light years and ask how quickly an actual spacecraft moves. Once the distance is known, travel time becomes a simple comparison between how far the destination is and how quickly a spacecraft can move. The result depends entirely on the speed placed into that comparison. Light makes the crossing in a little more than 4 years. Human machines move far more slowly, even when those machines are among the fastest objects our species has sent away from Earth. Voyager 1 provides a useful starting point because its journey is real. Launched in 1977, it traveled past the outer planets and continued outward until it crossed the heliopause, the boundary where the solar wind gives way to the surrounding interstellar environment. It is now moving through interstellar space at roughly 17 kilometers per second, relative to the Sun. 17 kilometers every second is an extraordinary speed by ordinary standards. At that rate, a vehicle could cross a continent in minutes. It could travel around Earth in less than an hour. But the space between stars does not operate on the scale of continents or planets. The speed that looks almost unimaginable near Earth becomes painfully small when it is placed beside a distance of roughly 40 trillion kilometers. Voyager 1 is not heading toward Alpha Centauri, and it cannot be treated as a spacecraft that missed the correct turn. Its trajectory was shaped by its planetary mission and by the gravitational encounters that carried it outward. The comparison is only a baseline. What would happen if a vehicle could move directly toward Proxima Centauri at a similar constant speed? Dividing the distance by that speed produces a journey lasting roughly 70,000 years or more. Depending on the exact distance, velocity, and reference used, the rounded result can fall near 70,000 to 75,000 years. Precision to the final year would be misleading. The important result is the scale. A machine moving as quickly as Voyager would need tens of thousands of years to reach the nearest star. The calculation also assumes that the craft is already moving at cruise speed and continues without interruption. It gives the journey no launch phase, no navigation correction, no failure, and no need to slow down at the other end. In that sense, 70,000 years is not a pessimistic story designed to make the distance frightening. It is a mathematical comparison built from favorable assumptions. A real mission, using similar performance, would face additional demands before arrival could mean anything more than passing the target. This exposes a common misunderstanding about the phrase interstellar space. When Voyager crossed the heliopause, it became the first human-made object to enter the space between stars. That achievement was historic, but the boundary lies close to the solar system when compared with Alpha Centauri. Entering an ocean is not the same as crossing it. Voyager has reached the environment that fills the Gulf, not the far shore. During a 70,000-year journey, the spacecraft would outlast every person present at launch. It would travel for far longer than the span covered by recorded human history. Languages, nations, technologies, and cultures could change beyond recognition, while the destination remained ahead. The problem would no longer be keeping a crew alive for a difficult expedition. It would be maintaining an entire moving human system across a duration normally associated with civilizations and species. One possible response is the generation ship. Instead of expecting the original passengers to arrive, a large habitat could carry a population whose children, grandchildren, and distant descendants continue the journey. The destination might eventually be reached, but the meaning of the mission would change. The people who accepted the departure would never see Alpha Centauri. Those who arrived would have been born inside the spacecraft and would inherit a purpose chosen thousands of generations earlier. The return problem would become even stranger. The original travelers could not come back because they would not complete even the outward crossing. Their descendants might decide to reverse course, but another journey of comparable length would follow. A simple doubling suggests around 140,000 years of motion. Yet even that is not a complete mission estimate. It ignores acceleration, braking, maintenance, changes of course, and whatever would be required to leave the destination system. The number only shows that an outward timescale, already beyond individual life, becomes more extreme when return is added. A generation ship, therefore, does not solve the title's question for the same people. It changes the subject from travelers completing a round trip to a population migrating between stars. That may be a possible form of distant human expansion, but it is not a journey in the familiar sense. No passenger can expect to leave Earth, arrive, and then see Earth again. The only way to preserve that familiar meaning is to shorten the travel time. A voyage lasting decades might remain within one long human life. A voyage lasting years would resemble exploration more closely. But reducing 70,000 years to decades cannot be achieved through a small improvement. The spacecraft must move hundreds or thousands of times faster than Voyager, eventually reaching a noticeable fraction of the speed of light. That requirement changes the problem. Spacecraft speed is not a setting that can simply be increased. Every kilogram must be accelerated, and the vehicle must carry an engine, a structure, protection, supplies, and often the material used to produce thrust. Reaching a greater speed demands a greater change in velocity, usually called delta V, and conventional rockets pay for delta V with propellant. The obvious answer is to build a larger rocket and load it with more fuel. Yet fuel is not weightless while it waits to be used. The rocket must accelerate the fuel needed for later acceleration, along with the tanks and systems that contain it. Adding propellant increases capability, but it also increases the mass that the earlier propellant must move. Voyager gives the first clear answer, then exposes the next problem. At demonstrated outbound speed, Alpha Centauri belongs to a timescale no individual can cross. To make the same people capable of arriving and returning, speed must rise enormously. The question is whether a rocket can gain that speed simply by carrying more fuel, or whether every added tank makes the escape from the 70,000-year answer even harder. The difficulty begins with the way a rocket moves. In space, there is no road for wheels to push against, and no surrounding air for an engine to pull through. A rocket accelerates by throwing material in one direction so that the vehicle moves in the other. That expelled material is reaction mass, and on an ordinary rocket it is carried as propellant. This produces an immediate bargain. The spacecraft can change its velocity only by expelling part of what it brought with it. How much change it can produce depends strongly on the speed at which the engine throws the exhaust backward. Faster exhaust allows each kilogram of propellant to provide more useful change in the spacecraft's motion. Slower exhaust means far more propellant must be carried for the same result. Engineers describe the required change in motion as delta V. It is not simply the speed shown during the middle of a journey. A mission may need delta V to leave its starting region, build cruising speed, correct its path, slow down, move within the destination system, depart again, and stop near Earth. Each change belongs to the same overall budget. A spacecraft that must return therefore needs much more than the velocity required to pass Alpha Centauri once. The trap appears when more propellant is added. Suppose a vehicle needs extra fuel for the later part of its acceleration. That fuel must be on board from the beginning. The earlier fuel must accelerate the spacecraft, its engines and tanks, the payload, and all the fuel that has not yet been burned. Adding propellant increases the vehicle's ability to change speed, but it also increases the mass that must be moved before that propellant can help. The same penalty repeats. Fuel added to move later fuel requires still more fuel at the beginning. Larger tanks need stronger structure. Stronger structure adds mass. Larger engines may be needed to manage the heavier vehicle, and those engines add mass as well. The relationship does not grow in a simple straight line. As the demanded delta V rises compared with the engine's exhaust velocity, the required ratio between initial mass and final mass grows extremely quickly. This is the central lesson of the rocket equation. The equation does not say that rockets cannot travel quickly. It says that gaining a very large change in velocity with a limited exhaust speed demands an enormous starting mass for every useful kilogram that remains at the end. At interstellar ambitions, the useful vehicle risks becoming a tiny remainder buried beneath layers of propellant, tanks, engines, and support structure. The effect can feel backward because fuel is normally understood as stored freedom. In a car, adding more fuel usually extends the journey without transforming the vehicle. A rocket carries its fuel while accelerating through the same journey, so the comparison breaks down. The first part of the burn must move everything intended for the last part. If the mission requires another burn after arrival, that future capability also travels as present mass. The vehicle is always paying to carry options it has not used yet. This is why a modest increase in required delta V can demand far more than a modest increase in propellant. The penalty comes from the relationship between what the engine can throw backward and how much motion the spacecraft must gain. Staging helps ordinary rockets control this burden. When one set of tanks is empty, the vehicle releases it instead of accelerating useless structure for the rest of the flight. Later stages then move a smaller mass. This strategy makes launch from Earth and travel around the solar system possible, but it does not remove the underlying relationship. Every stage must still be accelerated before it is discarded, and an interstellar craft cannot throw away the equipment it will need for arrival and return. Chemical rockets face the sharpest version of the problem because chemical reactions can give their exhaust only a limited velocity. Their performance is powerful enough to lift spacecraft away from planets and send probes across the solar system. It is nowhere close to what a crewed vehicle would need to reach a noticeable fraction of light speed with a realistic mass ratio. Making the chemical rocket larger mostly creates a larger version of the same bargain. A probe can reduce the burden by carrying little more than instruments and communication equipment. A crewed spacecraft cannot. Human beings need a pressurized living space, air and water systems, food or food production, power, temperature control, medicine, and protection. The vehicle needs spare parts, repair capability, sensors, computers, and redundancy for systems that cannot be allowed to fail. If artificial gravity or other long-duration measures are required, those structures also become part of the mass. Protection makes the connection even stronger. A shield is not separate from propulsion merely because its purpose is safety. Every protective kilogram must be accelerated to cruising speed and eventually slowed again. The same is true of radiators used to remove waste heat, reserve supplies kept for emergencies, and any equipment intended to support a second departure. A human mission is not an engine carrying passengers. It is a moving habitat whose entire physical existence must share the engine's velocity. This is why more powerful forms of propulsion attract attention. Nuclear reactions can release more energy per unit of fuel than chemical reactions. Fusion concepts aim to use the process that powers stars in a controlled engine. Antimatter offers an even greater theoretical energy density because matter and antimatter can convert mass into energy when they meet. In principle, such approaches could produce faster exhaust or reduce some of the propellant burden. But an energy-rich fuel is not automatically a working interstellar drive. The energy must be released at a controlled rate, directed into useful thrust, contained without destroying the vehicle, and managed without overwhelming it with waste heat. Some concepts still require reaction mass. Others require machinery, magnetic fields, fuel storage, or power systems that add mass. Antimatter must first be produced and stored safely. Fusion must be sustained and turned into efficient propulsion. These are engineering requirements, not details that disappear because the underlying physics permits high energy density. Nor does a better engine remove the return requirement. The vehicle may need to keep propulsion capability after decades of operation, or it may need infrastructure waiting at Alpha Centauri. Fuel reserved for the homeward journey must either be carried across the outward leg or obtained at the destination. Carrying it adds to departure mass. Producing it there assumes machinery, resources, energy, and reliability that must somehow arrive before the return can begin. The fuel problem, therefore, reveals a deeper boundary. Chemical propulsion cannot provide the required leap with a useful crewed payload, while advanced concepts remain incomplete and face their own mass, heat, control, and readiness limits. Yet even if one of those engines were granted, the craft would still be a massive object that must gain an extraordinary amount of motion. Velocity is not created for free. Whatever engine is chosen, energy must be transferred into the ship. The faster it moves and the more mass it carries, the greater that stored motion becomes. And reaching the destination at enormous speed would only create a flyby unless the vehicle could remove that motion again. The next question is therefore not only how to accelerate a ship, but how to pay for its speed twice, once to begin the journey and once more to make arrival possible. Grant the spacecraft an engine powerful enough to escape the chemical fuel trap. Let it accelerate beyond Voyager's speed, beyond every crewed vehicle ever built, until it reaches a meaningful fraction of the speed of light. The journey becomes shorter, but the problem does not disappear. It changes form. The vehicle is now carrying an extraordinary amount of energy in its motion. Kinetic energy is the energy an object has because it is moving. It depends on mass and speed. Increase the mass, and more energy is needed to reach the same velocity. Increase the velocity, and the energy rises even more sharply. At ordinary speeds, doubling velocity multiplies kinetic energy by 4. As a spacecraft approaches light speed, special relativity makes the increase steeper than that familiar rule suggests. It is useful to discuss the energy per kilogram before imagining any complete ship. Otherwise, an unstated payload mass can make a calculation appear more precise than it really is. Consider 1 kilogram moving at 1/5 of light speed, or 2c. Using the basic kinetic energy calculation, that kilogram carries about 1.8 quadrillion joules of motion. A relativistic calculation gives a slightly higher result, though at 0.2c the difference is still modest. That number belongs to only 1 kilogram. It is not the energy budget for a crewed mission. A human spacecraft would contain many kilograms of structure, engines, shielding, living space, equipment, supplies, and passengers. Every one of them must share the same cruise velocity. Multiplying the energy per kilogram by the full accelerated mass quickly produces a total beyond ordinary intuition. Even then, the result describes only the ideal kinetic energy stored in the moving vehicle. A real propulsion system would not turn all available energy into forward motion. Some would leave in exhaust, some would become heat, some would be consumed by supporting machinery, power conversion, beam losses, guidance, and control. The craft might also carry propellant or reaction mass whose movement requires further energy. The actual energy supplied must therefore exceed the clean kinetic figure. Waste heat creates a separate design burden because space offers no surrounding air or ocean to carry heat away. A spacecraft must move unwanted heat toward radiating surfaces and release it as light. Those radiators need area, material, protection, and a temperature they can survive. Increasing engine power without managing the rejected heat could damage the very vehicle the engine is meant to accelerate. This does not provide one universal limit, because different propulsion systems lose energy in different ways. It does show why quoting a fuel's theoretical energy density is not enough. A working drive must convert that energy, direct it, contain it, and remove what cannot become useful motion. Each support system adds mass, and that mass raises the energy needed for acceleration. The energy problem and the mass problem therefore feed one another instead of remaining separate engineering tasks. Even perfect propulsion would require the vehicle to reject heat. The rate at which this energy is delivered matters as well. A slow acceleration can reduce stress on passengers and structure, but it lengthens the period during which the engine must operate. A rapid acceleration shortens that phase, but demands enormous power and may create forces the vehicle or crew cannot tolerate. Whatever profile is chosen, the required change in motion remains. The engine must put the necessary momentum and energy into the ship. During the middle of the journey, this seems like success. At 0.2c, the distance to Alpha Centauri could be crossed in a little more than 20 years if acceleration and braking phases are temporarily ignored. That is an astonishing improvement over the Voyager baseline. Tens of thousands of years have become decades. But this calculation describes a craft passing through the destination's distance while still moving at 1/5 of light speed. At that velocity, crossing a local region takes very little time. The stars may be reached according to the map, yet the craft would not remain near them. It would enter the system, rush past its chosen target, and continue into interstellar space. Instruments might gather information during the encounter, but passengers could not treat the event as arrival. A destination is useful only if the vehicle can control its motion relative to what it came to visit. Stopping means removing the velocity that was so difficult to gain. Momentum must be transferred somewhere, and the kinetic energy must be redirected, converted, radiated, or carried away. The details depend on the braking method. But no method can simply declare the stored motion gone. An onboard engine could fire in the opposite direction. A sail might interact with light or another external force. Infrastructure already present in the destination system might supply a braking beam. Each option brings a new requirement. If the spacecraft uses its own propulsion to slow down, it must carry the necessary engine and resources during the entire outward crossing. That braking equipment contributes to the mass accelerated at departure. Propellant saved for arrival must also reach cruise speed before it can be used to remove cruise speed. The vehicle pays to carry the means of canceling the motion it is still struggling to acquire. The ideal scale of the braking task is comparable to the ideal scale of acceleration. The ship does not necessarily need to consume energy in exactly the same form or amount, because different systems exchange momentum and energy differently. But the physical state must change from a fast interstellar craft to a vehicle moving slowly enough within Alpha Centauri to operate there. The enormous kinetic energy difference cannot be ignored. This is why energy must be paid twice, even before return begins. First, the craft must be accelerated away from the solar system. Then its interstellar motion must be removed so that the crossing ends in arrival rather than a flyby. If it later travels home, another acceleration and another deceleration follow. The complete journey contains 4 major changes of motion, not one long period of cruising. Beamed propulsion offers a clever way to change part of this bargain. Instead of carrying the main energy source and a large fuel supply, a lightweight sail can be pushed by an intense beam produced near Earth. Photons carry momentum. When directed onto the sail, they can accelerate the craft while the massive power system remains behind. This separates the vehicle from much of the machinery generating its departure energy. Leaving the power source at home can reduce onboard mass, but it also reveals the asymmetry between departure and arrival. Earth can build and operate a beam because Earth already has infrastructure. Alpha Centauri has no human-built system waiting to perform the opposite task. A distant beam may become harder to keep focused as the craft recedes, and the same Earth-based installation does not automatically turn into a brake at the far end. A mission could imagine sending braking infrastructure first, using a different sail arrangement, carrying an onboard braking system, or finding resources after arrival. But each proposal must explain how the required equipment reaches the destination, slows itself, survives, and remains operational. Moving the braking problem into an earlier mission does not erase it. The first successful arrival must still be achieved somehow. For a tiny probe, accepting a flyby can be reasonable. The craft may collect measurements during a brief encounter and send them toward Earth. Removing brakes, a crew habitat, and return capability keeps the mass low enough for bold acceleration concepts. For human travelers, those removed functions are the mission. They need a ship that can stop, support life at the destination, depart again, and stop once more near Earth. Energy therefore becomes more than a question of whether an engine can make a vehicle move quickly. It decides what kind of journey the vehicle can perform. A high cruise speed can turn millennia into decades, yet without an equal commitment to controlling that speed, the supposed destination becomes a momentary crossing point. There is still one reason to accept such extreme cost. The faster the ship moves, the less time the journey may occupy for the people on board. But at these velocities, time itself must be described with more than one clock. Earth and the travelers will not necessarily agree on how long the crossing lasted. To know whether speed truly rescues a human lifetime, 2 clocks must leave Earth together and follow different paths. Begin with two identical clocks on Earth. Place one inside the spacecraft and leave the other beside the people who will watch it depart. Before launch, synchronize them. They agree on every second. When the engines begin their work, the clocks separate, and each follows a different path through space-time. Nothing unusual appears to the passengers beside their clock. Their hearts beat normally. Their thoughts do not slow. Meals, conversations, and mechanical processes proceed at the usual pace. The time shown by a clock traveling with them is called proper time. It is the duration directly experienced along the spacecraft's path. Earth uses another measurement. Observers there describe the distance to Alpha Centauri in their own frame and measure how long the ship takes to cross it. At the low speeds of ordinary life, Earth time and traveler time differ by so little that the effect can be ignored. At a significant fraction of light speed, they no longer agree. Special relativity describes the difference through a quantity called the Lorentz factor. Its value depends on the spacecraft's velocity compared with light. At rest relative to Earth, the factor is 1, and the clocks advance together. As relative speed rises, the factor rises. More Earth frame time then passes for each unit of proper time experienced aboard the craft. This language can create confusion because motion is relative. During a steady cruise, the passengers can describe Earth as moving away from them, just as Earth describes the spacecraft as moving away. Each frame has its own measurements of distant clocks and simultaneous events. The difference in accumulated time cannot be decided by choosing one viewpoint and declaring it stationary in an absolute sense. What matters is the path each clock follows between events where they can be compared. For the one-way examples here, departure and arrival provide those events, and the proper time along the spacecraft's path can be calculated without claiming that its passengers feel differently. Their shorter duration is not caused by a broken clock or a biological slowing mechanism. It is the geometry of space-time expressed through the motion between the departure and arrival events. This is why time dilation remains a prediction rather than an illusion created by delayed signals or by the time that light needs to carry an image back to Earth. The effect is real, but it is often exaggerated at speeds that merely sound relativistic. Consider the proposed cruise speed of 0.2 c, 1/5 of light speed. The Lorentz factor is about 1.021. If a simplified crossing takes a little more than 21 years in Earth's frame, the travelers experience only a modestly shorter duration, roughly 21 years, rather than a dramatic reduction to months or days. At 1/5 of light speed, the spacecraft is unimaginably fast by present human standards, yet its clock advantage remains small. Most of the shorter journey comes from moving quickly across the distance, not from strong time dilation. This distinction matters because the extreme engineering required to reach 0.2 c does not automatically give the crew an extreme separation from Earth's clock. Increase the speed to 0.6 c, and the difference becomes clearer. Ignoring acceleration and braking, a 4.25 light-year crossing would take about 7.1 years according to Earth. The Lorentz factor at that speed is 1.25, so the travelers would experience roughly 5.7 years. Both groups agree that departure and arrival occur, but they assign different elapsed times between those events. The example is not a mission schedule. A real spacecraft must spend time accelerating and later slowing down. Its velocity would change during those phases, so the clock difference would need to be accumulated across the complete journey. The simplified numbers isolate the effect of cruising speed. They show that relativity can save time for the crew, while also showing how much speed is required before the saving becomes substantial. From inside the ship, the same relationship can be described through length contraction. Earth and Alpha Centauri are moving relative to the travelers. In that frame, the distance along the direction of motion is shorter than the distance measured from Earth. At 0.6 c, the contraction matches the clock comparison. The travelers cross a shorter ship frame distance while their own time advances normally. This does not mean the stars physically move closer in some universal sense. There is no single viewpoint that owns the only correct distance and time. Earth measures its separation from Alpha Centauri and the journey duration in its frame. The travelers measure a contracted distance and a shorter proper time in theirs. The descriptions differ, but they predict the same departure and arrival events. Length contraction is therefore not an engineering shortcut that can be activated without speed. It is part of the relativistic description produced by the speed itself. The ship must still be accelerated. It must still carry its full mass, survive the crossing, and slow down. Earth does not see the external distance disappear, and the energy needed to create the motion is not cancelled by the traveler's shorter measurement. The temptation is to keep increasing velocity. If 0.6 c creates a useful difference, a speed much closer to light could reduce the traveler's elapsed time further. From their perspective, the interstellar gap could become dramatically contracted. A voyage covering many Earth frame years might fit inside a much shorter span of proper time. But light speed is not a reachable setting for a spacecraft with mass. As velocity approaches it, the Lorentz factor grows without limit. The energy required for each further increase becomes greater, and reaching light speed would require infinite energy. The ship can approach the boundary but never accelerate through it using known physics. This creates another exchange rather than a complete solution. Relativity offers the passengers a way to experience less time, but the strongest benefit appears only after the spacecraft has acquired the most difficult velocities. The energy problem grows. Braking becomes more severe. Every collision with material ahead becomes more energetic. The clock can be protected only by making nearly every other part of the mission harder. The two clocks also reveal why returning is not merely a matter of reversing a line. So far, the examples have described a one-way cruise at constant speed. The spacecraft departs in one direction and is compared with Earth from a distance. A round trip requires the vehicle to slow near Alpha Centauri, change its state of motion, accelerate toward the solar system, and finally reunite with the clock that remained behind. That reunion turns a comparison made from separate places into a direct result. The clocks can be placed beside each other again and read. The traveler's path includes acceleration, deceleration, and a change of direction, while Earth follows a different path through space-time. The famous twin comparison is resolved by those complete paths, not by saying that one clock is secretly wrong. Relativity therefore answers one part of the journey. Yes, sufficient speed can reduce the duration experienced on board. No, it does not make Alpha Centauri universally closer, and it does not allow a massive ship to reach light speed. Most importantly, shortening the traveler's time does not promise that the same amount of time passes on Earth. To understand what coming back would mean, the clocks must no longer be left in separate frames during a simple cruise. The spacecraft must stop, turn around, and return. Only then can the two clocks meet again, and reveal whether reaching the same planet also means returning to the same human world. A round trip is not one cruise followed by the same cruise in reverse. It is a chain of different physical states, and every change matters to the clocks, the engines, and the people on board. To return from Alpha Centauri, The spacecraft must complete at least 7 broad phases: accelerate away from Earth, cruise outward, brake near the destination, operate there, accelerate toward home, cruise inward, and brake again near Earth. Each phase also inherits the condition created by the one before it. The outward engine determines the speed that destination braking must remove. Braking determines whether the ship can remain and prepare to leave again. The homeward acceleration depends on whatever machinery and resources survived the first crossing. Final braking must work after the vehicle has operated for the full mission. A failure near the end cannot be corrected by success near the beginning. This makes return a test of continuity across the complete journey, not merely a repetition of its most impressive cruising phase at greater cost than before. The neat route line hides those phases because it shows position without showing motion. At the far end, the spacecraft cannot simply point its nose toward Earth and continue. If it is still moving rapidly away from the solar system, turning the hull does not reverse that velocity. The engine must first remove the outward motion and then build motion in the opposite direction. Turnaround is a major change of state, not an instant corner in space. This change is also central to the comparison between the two clocks. During a steady outward cruise, Earth can describe the spacecraft as moving, while the travelers can describe Earth as moving. That apparent symmetry often creates the so-called twin paradox. If motion is relative, why should the traveler return younger rather than Earth? The answer lies in the complete paths. The clock on Earth remains with Earth throughout the comparison. The traveling clock leaves, changes velocity, enters a different returning state of motion, and eventually comes back. The two paths through spacetime connect the same departure and reunion events, but they are not identical. Each clock records the proper time along its own path, and those accumulated durations can differ. Acceleration marks the fact that the traveler changes frames, but the final difference is not created by one magical instant during the turn. It depends on the complete trajectory, including how fast the ship moves and how long each phase lasts. A gentle turn lasting months and a rapid turn lasting hours would create different mission details. In either case, the outbound and inbound portions belong to one continuous traveler path that is not equivalent to remaining on Earth. When the spacecraft finally returns, no argument about distant observations is needed. Bring the clocks together and compare them directly. Both have functioned normally. Neither has lost time through damage. They have simply measured different amounts of proper time between the shared departure and reunion. The traveler can be younger than someone who remained on Earth because less time accumulated along the traveler's route. This does not prevent physical return. Relativity supplies no rule saying that a slower-than-light ship can depart, turn around, but never reach Earth again. If propulsion, braking, protection, and survival were solved, the trajectory could be completed. The deeper consequence is that solving the route does not force Earth and the travelers to share the same elapsed time. At moderate fractions of light speed, the difference across Alpha Centauri may be measured in years rather than centuries. At speeds much closer to light, the separation could become far greater. The crew might experience a manageable interval while Earth passes through a longer one. The exact result cannot be stated without a complete acceleration profile, cruise speed, destination stay, and return plan. There is no single twin paradox number for every Alpha Centauri mission. Even before the clocks reunite, the distance separates the travelers from Earth in another way. Information cannot cross the gap instantly. Radio, laser, or any other signal carrying a message is limited by the speed of light. From Earth to the Alpha Centauri system, a message needs more than 4 years to arrive. If Earth sends a question immediately after learning that the spacecraft has reached the destination, the travelers receive it years later. If they answer at once, the reply needs more than 4 additional years to return. A single exchange, therefore, spans more than 8 years, even before any time is allowed for decisions, repairs, or a carefully prepared response. This is not ordinary communication with a delay. It removes the possibility of real-time mission control. Earth cannot guide an urgent maneuver after observing a problem, because the observation is already years old when it arrives. Instructions sent in response describe a situation that may have changed years earlier. The crew must diagnose failures, choose actions, and accept consequences without waiting for help. Rescue becomes even less realistic. A replacement part, medical team, or second spacecraft cannot arrive on the timescale of an emergency. The travelers may continue sending information home, but communication becomes a record exchanged between separated worlds rather than a continuous conversation. Distance creates independence before relativity creates any large difference in age. That independence changes the requirements of the spacecraft. The crew needs authority, knowledge, spare systems, and repair capacity that planetary missions can distribute between a vehicle and teams on Earth. Decisions that would normally involve thousands of specialists must be anticipated on board or entrusted to systems operating without immediate supervision. Every added capability increases complexity and often adds mass. A physically successful return could therefore contain 2 forms of separation. The first comes from signal delay during the journey. The second comes from the different time accumulated by Earth and the travelers. The spacecraft may arrive beside the same planet from which it departed, yet the social connection to that planet may have weakened or disappeared. This consequence must be kept within what the physics supports. Relativity does not predict which nations, institutions, languages, or cultures will exist when the ship returns. It does not prove that Earth will become hostile or unrecognizable. Those are stories, not clock calculations. What physics establishes is narrower and more powerful. The elapsed times can differ, and no message can cross the distance faster than light. If the mission lasts long enough in Earth's frame, people known at departure may age or die before reunion. Organizations may change. The original purpose of the expedition may no longer carry the same meaning. These are reasonable consequences of elapsed time, but their details remain unknown. Returning home is therefore not only a navigation problem, it is an attempt to return to a shared present that the journey itself has divided. A self-sufficient spacecraft might accept this condition. Its crew could leave, knowing that Earth would become a distant source of delayed information rather than active support. They could treat the journey as an independent human project, equipped to complete its phases without rescue. That choice addresses the communication problem, but it deepens the engineering problem. Independence requires more equipment, more redundancy, more protection, and more resources. The attempt to save traveler time also creates a new physical environment. At low speed, the sparse gas and dust between stars appear almost empty. At a significant fraction of light speed, the ship meets the same material with far greater relative energy. Particles too thinly spread to feel like an atmosphere begin arriving like radiation. Turnaround therefore delivers a crucial answer. A return path is allowed, and the 2 clocks can meet again. Yet the reunion may occur after different amounts of lived time, following years without immediate guidance or rescue. The ship can aim for the same coordinates while losing the shared time that once made those coordinates home. and the faster it travels to protect the crew's clock, the more violently it encounters the space ahead. Before any return can be discussed as a human event, the vehicle must first survive 4 light-years of a vacuum that is no longer harmless at the speed required. Interstellar space is often described as a vacuum, and compared with any atmosphere on Earth, that description is reasonable. The particles between stars are spread extraordinarily thinly. A person could never feel them as wind. A stationary object would not experience anything resembling weather. But the danger changes when a spacecraft crosses that environment at a significant fraction of light speed. The ship does not meet one particle and then stop. Its forward surface sweeps through a long column of space, extending for more than 4 light-years. Every small area facing the direction of travel encounters whatever gas and dust lies along that path. Low density is therefore only one part of the problem. The other parts are distance, exposed area, and relative velocity. The situation can be understood without imagining a hidden cloud. There need not be any sudden region where the spacecraft enters thick material. A nearly uniform trickle can matter, because the exposure continues through years of motion and across the full front of the vehicle. Each square meter collects its own history of impacts. A larger habitat presents a larger forward area unless its shape and orientation reduce that exposure. This means the hazard scales not only with how fast the craft moves, but also with how much surface it places in the stream and how long that surface must remain safely functional. From the spacecraft's frame, the interstellar material rushes toward the vehicle. A particle that would be almost harmless at low relative speed carries far more kinetic energy when the closing velocity reaches 0.2 c. In one model, used to study relativistic spacecraft, incoming protons at this speed carry about 19 million electron volts of energy, placing them in the tens of MeV range. The unit is less important than the change in behavior. These protons no longer resemble a cold, thin gas gently touching the spacecraft. They arrive as energetic particles capable of ionizing material. They can enter surfaces, transfer energy, disturb atoms, and contribute to radiation exposure. A steady stream across years of flight creates a cumulative engineering problem even when no single proton threatens the entire vehicle. When gas particles enter a material, some can become embedded beneath the surface. This is implantation. Accumulated particles may create pressure and defects inside the material, contributing to blistering. Repeated impacts can also knock atoms from the surface in a process called sputtering. Over time, exposed layers can erode, weaken, or change their physical behavior. The exact damage depends on the material, particle type, energy, angle of impact, shield thickness, and surrounding design. Models help engineers estimate these effects, but humanity has not flown a spacecraft at 0.2 c through the interstellar medium. The result is a strong physical warning supported by particle behavior and material studies, not a direct report from an Alpha Centauri mission. Radiation is not limited to the particle's first impact. When energetic material strikes a shield, it can create secondary particles or radiation inside the protective structure. A thick barrier can absorb more incoming energy, but shield design must control what is produced during that absorption. Protecting the crew is not simply a matter of placing the largest possible slab in front of the ship. Dust creates a related but different hazard. Gas is made mostly of individual atoms, ions, and small particles spread through space. Dust grains contain far more mass in one object. At ordinary spacecraft speeds, dust already causes erosion and impact concerns. At a large fraction of light speed, Even a tiny grain carries concentrated kinetic energy because the relative velocity is enormous. This does not mean that every grain is guaranteed to destroy the spacecraft. Risk depends on how many grains occupy the route, how large they are, what they are made from, and where they strike. The distribution of larger grains in interstellar space is not known perfectly. A responsible design must therefore handle both the cumulative exposure that is expected and the lower frequency impacts whose exact likelihood is uncertain. The distinction matters because gas and dust may require different forms of protection. Charged particles can, in principle, be influenced by electric or magnetic fields. A spacecraft might try to deflect some incoming ions before they touch its structure. But creating and maintaining strong fields requires equipment and power, and the particles may still create radiation or interact with surrounding systems. Neutral matter is harder to redirect electromagnetically. A dust grain without a useful charge does not simply curve away because a magnetic field is present. The craft may need physical protection, forward shields, separated layers, sacrificial material, or structures designed to spread the energy of an impact. Those layers must remain stable during acceleration, cruise, braking, and the return journey. A sacrificial shield accepts that its outer surface will be damaged. Instead of demanding that one perfect layer remain unchanged, the design provides material that can erode while protecting critical systems behind it. This may be practical for a limited mission, but the amount of material depends on the expected exposure. A round trip doubles the long interstellar crossings and requires protection to remain sufficient after the outward leg. The spacecraft's orientation also becomes critical. Most of the high-speed exposure arrives from the direction of motion, so the strongest protection can be concentrated forward. Yet the ship must maneuver, brake, and reverse direction. The surface that leads during the outward journey may not lead during the return. A design could rotate the vehicle or provide protection at both ends, but either choice creates structural and operational demands. Detection offers only a partial answer. At relativistic closing speed, the time between noticing an object and reaching it can be extremely short. Small grains are difficult to detect at great distance, and a rapid turn by a massive crewed spacecraft is not simple. Clearing a path in advance or sending precursor probes may reduce uncertainty, but those systems must operate across the same enormous distance. Every protection method returns the mission to the mass problem. A thicker shield adds kilograms that must be accelerated to cruise speed. Field-generating equipment adds power systems, structure, and cooling. Replaceable or sacrificial layers add stored material. Redundant forward surfaces add complexity. The engine must move all of it, and the braking system must later remove all of its motion. Reducing speed would ease many of these hazards. Incoming particles would carry less energy, shielding demands could change, and detection time would improve. But slowing the spacecraft lengthens the journey, increasing the duration for which people, machines, and life support systems must function. The choice is not between a dangerous speed and a safe speed. It is a trade between different kinds of risk. Increasing speed to strengthen time dilation produces the opposite exchange. The travelers may experience less time, but the material ahead becomes more energetic in their frame. The shield must become more capable, just as propulsion becomes more demanding. Protecting the crew's clock and protecting the crew's body pull the design in conflicting directions. The interstellar medium, therefore, does not form an impenetrable wall. Physics does not prove that every fast spacecraft must be destroyed. What it does establish is that empty space cannot be treated as nothing. Across 4 light-years, sparse gas creates radiation and erosion, while uncertain dust adds concentrated impact risk. Surviving requires a deliberate forward defense, whose mass and durability become part of the complete mission. And the shield protects more than passengers seated in a cabin. Behind it must operate an atmosphere, a water cycle, food systems, power generation, medicine, repairs, computers, and every other function that Earth normally provides. The next question is no longer whether one material can survive the crossing. It is whether an entire living system can remain healthy and repairable long enough to arrive, return, and keep its human purpose intact. Behind the forward shield, the spacecraft must carry a small piece of Earth. Not soil and oceans in the literal sense, but the connected functions that allow human life to continue. A cabin with stored oxygen and packaged food may support a short mission. An interstellar crew needs an environment capable of renewing itself, while the nearest outside help remains years away by signal and far longer by spacecraft. Air must be kept within safe limits. Carbon dioxide and other unwanted gases must be removed. Oxygen must be stored, recovered, or produced. Water must be cleaned and circulated. Waste must be processed without allowing harmful material to accumulate. Food must either be carried for the required duration or produced through systems that need light, nutrients, water, space, and careful control. These functions cannot be treated independently. Food production affects water and power demand. Temperature control affects equipment and biological health. Waste processing influences air and water quality. Power failure can stop pumps, fans, sensors, lighting, and communications at once. A crewed ship is therefore a traveling ecology joined to an industrial machine. Recycling can reduce the amount of stored material, but recycling is not the same as perfect closure. Each cycle may lose a small amount. Filters become saturated. Chemicals become contaminated. Materials move into forms that are difficult to recover. A loss that is harmless over months may become serious over decades, and a system intended for generations faces an even stricter balance. Present crewed spacecraft do not provide a complete demonstration of this independence. They operate near enough to Earth to receive constant support, detailed instructions, and, in many cases, replacement supplies or components. Large teams on the ground monitor systems and help diagnose problems. Even when astronauts perform repairs themselves, the knowledge and logistics of Earth remain part of the mission. An Alpha Centauri crew cannot use that model. A message asking for help takes more than 4 years to reach Earth, and an answer takes more than 4 additional years to return. No urgent failure can wait for that exchange. A replacement component sent after the problem begins would be useless on an emergency timescale. The ship must carry the means to understand and respond before departure. That requirement includes sensors capable of detecting slow changes before they become crises. It includes tools, spare parts, repair instructions, and people or automated systems able to use them. Components may need to be rebuilt rather than replaced. Manufacturing equipment could reduce the need to store every possible spare, but the machinery itself needs raw material, power, maintenance, and backup. Redundancy protects against a single failure by providing another way to perform the same critical function. 2 pumps are safer than 1, only if the second pump remains independent and usable. Shared power lines, software, cooling systems, or design flaws can defeat apparent redundancy. True resilience may require different methods, separated systems, and enough stored capacity to continue while repairs are made. Time also changes equipment, even when nothing dramatic happens. Seals can lose flexibility. Surfaces can wear. Electronics can suffer damage. Moving parts can slowly drift from their intended performance. Software can continue running while sensors feeding it become inaccurate. A long mission must therefore detect gradual decline, not only sudden failure. Maintenance becomes a permanent process of measurement, replacement, calibration, and learning. The crew must know which change can be tolerated, which part can be repaired, and which resource cannot be spent. Reliability over decades is not simply the absence of accidents. It is the ability to manage continuous aging without allowing many small problems to combine into one irreversible loss. Every layer of safety has a physical cost. Backup machines add mass. Spare material adds mass. Additional pipes, cables, sensors, computers, and protective separation add mass. A larger crew may provide more skills and genetic or social resilience, but it also increases the demand for living volume, food, water, air processing, and medical care. Propulsion must accelerate this complete system, not an abstract passenger count. Human health adds requirements that machinery alone cannot settle. The crew needs protection from radiation, a suitable physical environment, exercise, or another response to prolonged low gravity, medical capability, and a stable supply of essentials. A mission lasting decades must plan for ordinary aging and health problems, as well as emergencies. A mission lasting generations must also confront reproduction and development in an environment never tested across that duration. These are not predictions of certain disaster. There is no evidence proving that humans must fail in a sufficiently well-designed closed habitat. The honest conclusion is that no complete system has been demonstrated for anything close to the isolation, duration, and repair burden of an interstellar round trip. The mission would depend on technologies and operating experience that do not yet exist as one proven whole. Speed appears to offer relief. A faster crossing reduces the time during which people consume supplies and equipment must function. It reduces the number of years available for small losses to accumulate. It may allow the original crew to complete the journey rather than handing it to descendants. But the faster ship faces the energy, braking, heat, and particle hazards already established. Slowing down changes the burden rather than removing it. Lower relative speed can reduce the energy carried by incoming gas and dust. It can ease some shielding and propulsion demands. Yet every saved unit of speed returns as additional mission time. Life support must operate longer. More maintenance cycles are required, and the chance that rare failures occur somewhere during the journey grows. There is no neutral speed that minimizes every problem. High speed stresses propulsion and protection. Low speed stresses biology and reliability. The design must choose where to carry the difficulty. A compromise velocity may distribute the risks, but it cannot make the ship independent of them. Return makes the endurance requirements stricter. Systems cannot be designed only to reach Alpha Centauri at the edge of their useful life. Braking, destination operations, preparation for departure, the inbound crossing, and final arrival near Earth remain. A machine that survives the outward journey but cannot operate afterward has completed a one-way experiment, not a round trip. The crew's ecosystem must therefore be repairable rather than merely durable. It must preserve knowledge and operational skill. It must be able to recover after damage, adapt to failures that were not predicted exactly, and continue without treating Earth as an active workshop. That level of independence begins to resemble a settlement contained inside a vehicle. The mass of this settlement closes the loop with propulsion. Every system that makes survival more believable makes acceleration and braking harder. Reducing the vehicle's mass makes high speed more believable, but removing habitat, shields, repairs, and people also removes the purpose of a crewed mission. This trade-off is visible in the most famous proposal for a rapid journey to Alpha Centauri. Its designers do not attempt to accelerate a protected human ecosystem. They pursue speed by shrinking the spacecraft until nearly every function discussed here disappears. The result shows both how an interstellar crossing might begin and why crossing the distance is not yet the same problem as bringing people home. Breakthrough Starshot begins by accepting a severe rule. If a spacecraft must move extremely quickly, make the spacecraft extremely small. The program is not a plan to place passengers inside a faster version of an ordinary ship. It is a research and engineering effort intended to test whether light can drive gram-scale robotic craft toward another star. The basic concept separates the energy source from the vehicle. A powerful array near Earth would produce a concentrated beam of light. That light would strike a thin reflective sail attached to a tiny package of electronics. Photons carry momentum, so their repeated arrival would push the sail and accelerate the craft without requiring it to carry the large power source producing the beam. The stated ambition is remarkable. A nanocraft might be accelerated to around 1/5 of light speed. At roughly 0.2 c, it could cross the distance to Alpha Centauri in about 20 years of flight. Instead of waiting tens of thousands of years for a Voyager speed machine, humanity could receive data from a neighboring stellar system within a human career. These numbers describe a goal, not an accomplished flight. No Starshot craft has reached 0.2 c or completed an interstellar mission. The program seeks proof of concept for technologies that must work together. An enormous light source, a sail with very low mass, stable acceleration, accurate navigation, durable electronics, communication across light years, and survival through the interstellar environment. Its importance lies partly in how clearly it exposes the interstellar trade. The energy-generating machinery stays near Earth, where it does not need to be accelerated. The spacecraft is reduced to grams, so far less mass must gain the required motion. The sail uses incoming light rather than carrying a conventional supply of propellant for the acceleration phase. Every choice attacks the mass problem directly. But those choices also define what the mission is not. A gram-scale nanocraft has no pressurized habitat. It carries no air, water, food, medicine, or human passengers. It does not contain an industrial repair system or decades of spare parts. It cannot provide the large protected volume needed by a crew. Its possible success depends on having almost none of the functions that made the human spacecraft massive. Protection is also constrained by the same mass limit. A tiny craft may use careful orientation, materials, redundancy across many launched probes, or other strategies to improve the chance that useful instruments survive. It cannot simply add a thick shield without changing the acceleration problem. Launching many small craft can allow some failures while preserving the mission, an option unavailable when every passenger is concentrated inside one habitat. Most importantly, the proposed journey is a flyby. The craft would approach Alpha Centauri while still moving at an enormous speed, gather observations during its passage, and continue onward. It would not enter orbit, land, establish infrastructure, or wait inside the system. It would not carry the equipment needed to cancel its interstellar velocity. For scientific reconnaissance, a flyby can still be valuable. Instruments might return images or measurements from a distance, No human probe has crossed. The fact that the encounter is brief does not make the information meaningless. A successful mission would represent a profound advance in propulsion, miniaturization, navigation, materials, and communication. Even returning data is not automatic. The nanocraft must observe while moving rapidly, decide what information matters, point a transmitter toward the solar system, and send a signal across more than 4 light-years. The tiny vehicle has limited power and antenna capacity, while Earth must detect its faint transmission years after the encounter. These communication demands belong to the proposed mission, but they still differ from carrying people. A probe may complete its purpose by surviving long enough to measure and transmit. A crew must remain alive throughout every phase. Yet the same achievement would not demonstrate human arrival. The nanocraft has no destination braking, no local operations lasting years, and no way to prepare for departure toward Earth. It does not reverse course. It does not return. Removing those stages is one reason the outward speed becomes easier to imagine. The difference cannot be repaired by replacing the tiny electronics with a crew cabin while keeping everything else unchanged. Scaling from grams to a human habitat is not linear. More mass requires more momentum from the beam. The sail must carry a larger load while remaining stable and reflective. Acceleration forces, heating, beam focus, and structural control change with the system's size and design. Then the removed functions return. A crew needs shielding, life support, power, repairs, living volume, and braking. Those systems increase mass, which increases the beam and sail requirements. If onboard propulsion is added for destination braking, its machinery and resources also need acceleration. If the return journey is included, another source of momentum and energy must be available after arrival. Starshot therefore does not fail the comparison. It succeeds at defining a different mission. It asks how little machinery can cross the gap quickly enough to gather data, while a human round trip asks how much civilization-supporting machinery can be carried, protected, stopped, restarted, and brought home. Both concern Alpha Centauri, but they occupy different parts of the design space. The contrast also explains why a real robotic precursor would be useful. Tiny probes could improve knowledge of the destination and the material along the route. They could test communication and navigation ideas. What they could not do by themselves is construct the heavy infrastructure required to stop and relaunch a crewed vehicle. Information can reduce uncertainty, but it cannot substitute for brakes, shields, fuel, or a living environment. The proposed 20-year crossing must therefore be described precisely. It is not a 20-year human voyage, a 20-year arrival into orbit, or 1/2 of a 40-year round trip. It is the flight time of a proposed gram-scale flyby traveling near the target speed. Each added mission function changes that result. This precision protects the genuine achievement rather than diminishing it. Interstellar travel is difficult enough that sending any working spacecraft to Alpha Centauri would be historic. A concept does not need to carry people to matter, but its promise cannot be used as evidence that the barriers facing people have already been solved. Starshot makes the hidden bargain visible. To approach relativistic speed with a plausible concept, leave the main power system at home, reduce the craft to grams, accept a brief encounter, and give up stopping and return. The proposal gains speed by removing nearly everything that defines a human journey. The next test is to restore those missing functions one by one. Add the crew, the shield, the habitat, the brake, the ability to operate after arrival, and the means to accelerate toward Earth. Then ask whether advanced propulsion, destination infrastructure, or any proposed shortcut can close every line of that complete round-trip ledger without quietly changing the meaning of return. Restore everything that a gram-scale flyby was able to remove, and the mission changes immediately. Begin with a protected habitat rather than a tiny instrument package. Add human passengers, life support, repair capability, power, communication, navigation, and enough shielding to face the interstellar medium. Then require the craft to stop, operate, leave again, and return to Earth. The complete ledger begins before departure. A propulsion system must accelerate the entire inhabited vehicle while controlling heat and keeping forces within acceptable limits. During the outward crossing, the shield and habitat must remain functional without immediate help. Navigation must keep the craft on a path accurate enough for arrival after years of travel. Near Alpha Centauri, the vehicle must remove its interstellar velocity. It must then operate inside the system rather than rush through it. Engines, power systems, computers, medical equipment, and life support cannot reach the destination already exhausted. They must retain enough useful life for local decisions, repairs, and preparations for the journey home. Homeward departure needs another source of momentum and energy. If fuel or reaction mass was carried from Earth, it increased the outward mass and the energy needed for the first acceleration and braking. If it is collected or manufactured after arrival, the mission requires equipment capable of finding resources, processing them, storing them, and verifying that the resulting propulsion system is safe. The inbound crossing repeats the exposure to gas, dust, radiation, isolation, and equipment aging. The shield may now be partly eroded. The crew and habitat have already operated for the entire outward mission. Finally, the spacecraft must remove its homeward velocity near Earth. Passing the solar system at relativistic speed would not count as coming back in any useful sense. Return is therefore not produced by doubling one travel time number. It is a sequence in which every phase depends on the survival and success of the phases before it. A design that closes 7 lines of the ledger but leaves the 8th unanswered does not complete the round trip. This standard prevents partial solutions from being mistaken for complete ones. A drive may reach the desired speed, but lack a brake. A brake may work only with infrastructure absent from the destination. A habitat may support people for decades, but be too massive for the propulsion system. A shield may protect the outward-facing surface while leaving no arrangement for the reverse journey. None of these failures proves that the component lacks value. It means that mission claims must match what the component enables. Interstellar research can advance through probes, materials, engines, sails, life support tests, and robotic construction without any experiment demonstrating a human round trip. The ledger is not a reason to dismiss progress. It is a way to keep progress from being stretched beyond its evidence and to identify which unsolved requirement becomes the next problem. Advanced propulsion may improve important parts of this picture. A fusion engine could, in principle, offer a much higher exhaust velocity and energy density than a chemical rocket. Antimatter could release still more energy from a small amount of stored material. These possibilities explain why interstellar travel is not treated as a simple violation of physics. But neither label represents a finished crude drive. Fusion must be initiated, controlled, supplied with suitable fuel, and turned efficiently into directed thrust. The engine and its supporting systems have mass and produce heat. Antimatter must first be created, then stored without contacting ordinary matter, and released in a controlled way. Its energy must become useful momentum without destroying the vehicle. Higher energy density can reduce the mass of an energy source, but it does not remove the habitat, shield, radiators, engines, reaction mass where required, or destination brakes. It does not make reliability automatic. It changes some entries in the ledger while leaving others in place. Another proposal is to build infrastructure at Alpha Centauri before people depart. Robotic missions could deliver a braking beam, power station, fuel plant, communication system, or shelter. The crew would then arrive at a destination prepared to receive them, and perhaps equipped to send them home. This approach could be valuable, but it creates a first arrival problem. The infrastructure must cross the same interstellar gap. Unlike a flyby probe, it must brake and remain in the system. It must deploy, generate power, repair or preserve itself, and operate after years without human technicians. If many shipments are needed, each must solve its own navigation and arrival problem. Infrastructure moves risk into earlier missions and may distribute it across many launches. It does not make the first successful delivery free. Before it can help a crew stop, something capable of stopping and constructing must already have reached Alpha Centauri. A generation ship changes a different line. It reduces the need for one human lifespan to cover the outward journey by allowing descendants to continue it. This may make slow migration imaginable, but it does not bring the original travelers back. It replaces an expedition completed by the people who depart with a long settlement project whose final members were born during the crossing. The title's question concerns anyone who travels and returns. Changing the identity of the travelers may create a form of interstellar expansion, but it does not close the same-person round-trip ledger. It solves duration by changing who receives the answer. The most dramatic shortcuts attempt to change space-time itself. Mathematical work in general relativity allows researchers to examine unusual geometries, sometimes described as warp motion or wormholes. Such ideas are important because they test what the equations permit and expose deep connections between gravity, energy, and causality. But a mathematical geometry is not a vehicle. A usable shortcut would require a way to create, control, stabilize, and navigate the necessary space-time structure. Many proposals involve negative energy or other conditions that have not been shown to exist in the required macroscopic, controllable form. Instability and causality problems remain serious concerns. Small quantum effects associated with negative energy do not provide a warehouse of exotic material ready for construction. A written metric does not specify an engine, power supply, hull, control system, or safe method of entering and leaving it. Wormholes face the same gap between mathematical possibility and physical engineering. No traversable human pathway has been observed or built. This does not prove that every future breakthrough is impossible. Science should not turn present ignorance into a law against discovery. New physics or engineering may alter what can be attempted. The correct standard, however, is not whether an idea can be named or represented in an equation. It is whether the idea closes the actual mission requirements without hiding them inside an assumption. For any proposed solution, the questions remain concrete. What accelerates the crude mass? What protects it? How does it slow down? What keeps people alive? What operates after arrival? What supplies the return? How does the ship survive the second crossing and stop near Earth? What time passes for the crew and for home? No current concept answers all of these questions, as one demonstrated architecture. Some solve speed by reducing mass. Some improve theoretical energy density. Some accept a one-way settlement. Some assume infrastructure that must first be delivered. Others remain mathematical possibilities without a construction path. The ledger does not identify one universal wall across interstellar space. It reveals something more difficult to defeat. The requirements are coupled. Solving one line often makes another harder, and removing a requirement changes the mission being claimed. With every line now visible, the investigation can finally return to the word never. The evidence does not support a careless declaration that physics forbids all return. It supports a more exact answer about physical possibility, engineering reality, and the meaning of arriving back at the same planet after the clocks have separated. The word never can now be tested against the complete journey rather than against one dramatic obstacle. The distance has been measured. The speeds, energy, clocks, hazards, life support demands, braking problem, and missing return infrastructure have been placed into the same ledger. Together, they produce an answer more precise than the title first appears to promise. The physical verdict comes first. Known physics does not ban a round trip to Alpha Centauri. A spacecraft with mass cannot reach or exceed light speed, but it may follow a slower-than-light path from Earth to another star and back. Special relativity permits that trajectory. It changes the energy required and the time recorded along different paths, but it does not close an invisible door behind the traveler. So the strongest literal version of never is false. Nature has not supplied a theorem saying that anyone who reaches Alpha Centauri is physically unable to point homeward and return. If every necessary system existed, the route could be traced in both directions. The engineering verdict is different. At the kind of outbound speed humanity has demonstrated with Voyager, the outward crossing alone lasts roughly 70,000 years or more. The original travelers do not arrive. A generation ship might carry descendants across the distance, but it changes who completes the journey and extends the return problem across an even longer human history. Compressing that timescale requires a leap to a meaningful fraction of light speed. The craft must accelerate every kilogram of engine, structure, shielding, habitat, supplies, and passengers. It must control the heat and energy involved. It must survive gas and dust, made dangerous by relative velocity. Then it must remove its interstellar motion at Alpha Centauri instead of merely passing through. After arrival, the vehicle must remain functional, obtain the means to depart, accelerate again, cross the same hazardous distance, and brake near Earth. Life support and repair systems must survive the entire sequence without rapid help. No demonstrated propulsion system, habitat, shield, brake, or mission architecture performs all of these tasks together. The best-known proposal for a rapid crossing makes the contrast clear. Breakthrough Starshot explores whether gram-scale robotic craft might be pushed toward approximately 0.2 c for a flyby lasting about 20 years. The concept gains speed by leaving the main power source near Earth and removing people, heavy shielding, destination braking, long-term operations, relaunch, and return. That is not a flaw in its scientific purpose. It is evidence that a fast probe mission and a crewed round trip are different achievements. Scaling from grams to an inhabited, repairable vehicle is not a matter of enlarging the same design. The added functions change the mass, energy, heat, sail, shielding, braking, and reliability requirements together. This produces the practical meaning of never. Under demonstrated technology and foreseeable engineering, there is no complete path that carries the same human travelers to Alpha Centauri, stops them there, keeps them alive, and brings them back within a meaningful human timescale. Current machines are too slow, while faster concepts remove the very functions required for human return. The temporal verdict adds another meaning. Suppose future engineering somehow produces a spacecraft capable of extreme relativistic travel. Time dilation could allow the crew to experience less time than Earth. Length contraction could make the distance shorter in the traveler's frame. These effects may protect the travelers from spending the full Earth-measured duration on board. But they do not preserve a shared present. Earth continues along its own path through space-time. When the spacecraft turns around and the clocks eventually reunite, more time may have passed for Earth than for the travelers. The ship can return to the correct planet while arriving in an era separated from the one it left. How large that separation becomes depends on the mission. At moderate relativistic speeds, it may be years. At speeds extremely close to light, it could be much greater. Physics does not predict the culture waiting on Earth, but it does establish that the clocks need not agree and that messages cannot erase the separation by traveling faster than light. There are therefore three ways the return can fail. At attainable speeds, the original travelers do not survive the duration, so anyone who arrives is not anyone who departed. With sufficiently relativistic technology, the travelers may physically return, but not to their original human era. And in the present, no demonstrated architecture can complete all phases of the mission at all. These are not three unrelated objections. They emerge from the same coupled system. Slowing down reduces energy and collision severity, but lengthens the burden on biology and machinery. Speeding up reduces travel time, but raises energy, heat, braking, and shielding demands. Adding protection and redundancy improves survival, but increases mass. Removing mass improves acceleration, but strips away crew safety, stopping, and return. Every local solution moves pressure somewhere else. Better propulsion does not supply a destination brake automatically. A stronger shield must itself be accelerated. A shorter onboard journey requires a more extreme velocity. Infrastructure at Alpha Centauri must first cross the distance and stop. A generation ship preserves a population by surrendering the original travelers. A mathematical shortcut does not become a machine because the equations can describe it. The one-way character of the journey is therefore not a wall. It is an outcome created by the interaction of requirements. No single line of the ledger proves eternal impossibility. Together, the lines explain why a mission can become physically imaginable while remaining practically unavailable and humanly irreversible. This is the scientifically defensible answer to the title. Anyone who travels to Alpha Centauri is not forbidden by relativity from returning. But with technology we possess, or can presently turn into a complete design, the journey cannot bring the same people back within the world they knew. Either the crossing outlasts them, the mission cannot stop in reverse, the habitat cannot be shown to endure, or the clocks separate their return from their original time. The word never must remain conditional. It means under known physics as we can engineer it, under demonstrated capability, and under the ordinary meaning of a traveler leaving home and later coming back to it. It does not mean that science has mapped every future discovery. It means that every honest route available now becomes a flyby, a migration, a settlement, or a departure whose return cannot be promised. That conclusion is stronger than claiming a mysterious force blocks the way. It identifies which conditions must change before return becomes credible and prevents possibility in principle from being confused with capability in practice. Once that distinction is accepted, the journey changes category. It is no longer simply a longer expedition. The question is not only whether humans can reach another star, but whether the first people who attempt it would be explorers expecting reunion or founders accepting that the world behind them may continue without them. The conclusion belongs to the present, but it should not be mistaken for a claim about all time. Engines once considered impossible to build have become ordinary. Materials, computation, medicine, automation, and energy systems may develop in ways that cannot be mapped in advance. A future discovery could alter one or several lines of the interstellar ledger. Foreseeable does not mean forever. Saying that no complete crude round-trip architecture exists is not the same as saying that none can ever exist. Science becomes weaker when uncertainty is hidden, whether that uncertainty is used to promise an easy future or to declare permanent defeat. Yet humility about the future does not erase what is known now. Alpha Centauri will not become closer because a better engine is invented. Signals will still require years to cross the gap unless our understanding of causality changes at a fundamental level. A vehicle will still need to gain and lose momentum. Its energy, heat, structure, and payload will still have to be accounted for rather than wished away. The space between stars will still contain material. A ship will still need to interact with that environment and protect whatever it carries. People will still require a functioning habitat for however much time they experience. If the travelers follow a path through space-time different from Earth's, the elapsed time along those paths will still matter when anyone speaks about return. Future technology may change the size of each burden. Better propulsion could shorten the journey. Better materials could reduce shielding mass. More complete recycling and repair could extend a habitat's life. Robotic missions could prepare infrastructure before people leave. None of these possibilities should be dismissed. But a complete mission will exist only when the possibilities work together rather than appearing separately in designs and equations. If that day comes, the people who depart may need a different understanding of their journey. Exploration within the solar system allows travelers to imagine Earth as a base. Messages arrive after delays that can be planned around. Missions can be supported by institutions that remain connected to daily decisions. Even distant crews belong to a shared human present. Alpha Centauri breaks that pattern. Communication becomes an exchange between different years. Rescue cannot follow an emergency. Supplies cannot be requested after they are needed. The travelers must carry not only equipment, but also the authority and knowledge to make decisions whose consequences Earth will learn about much later. Their spacecraft would therefore be more than transportation. It would be a community contained inside a machine, responsible for its air, water, food, repairs, health, memory, and future. The crew could not behave like passengers waiting to be delivered. They would have to preserve the conditions under which passengers, engineers, doctors, and decision-makers could continue to exist. This begins to resemble founding more than visiting. A visitor expects the place left behind to remain available as a center of life. A founder carries enough continuity to begin somewhere else. The first human beings to cross the gap may leave Earth not because they know they can return, but because they accept that survival and purpose must continue without the promise of reunion. That interpretation is not a result derived from an equation. Physics can describe distance, energy, velocity, signals, and elapsed time. It cannot predict what future travelers will value, how they will organize themselves, or whether they will consider departure a sacrifice, an opportunity, or something for which we have no current word. Nor can physics tell us what Earth will mean to them after years away. It may remain the source of language, history, and identity. It may become a place known mostly through stored records and delayed messages. A later generation born during the journey may understand it differently from those who remember standing beneath its sky. These possibilities should remain restrained because no crew has faced them. Inventing their emotions would replace evidence with a story. What can be said is that distance and signal delay force independence, while relativistic time can weaken the shared present. The social meaning grows naturally from those conditions, even though its exact form remains unknowable. This is why the question of return reaches beyond engines. A spacecraft might cross every kilometer back to Earth and still fail to restore what departure ended. Home was also a network of living relationships. It was a common sequence of events, experienced closely enough for action and response to belong to the same moment. It was the ability to leave while expecting that the people who watched the departure could also witness the return. Interstellar distance stretches that expectation until it breaks. At slow speeds, lifetimes and generations pass before arrival. At extreme speeds, the travelers may protect some of their own time while Earth continues into its future. In both cases, the route back points toward a location more reliably than it points toward the world remembered at launch. This does not make the journey meaningless. An irreversible act can carry knowledge, hope, responsibility, and purpose. Robotic probes may extend human sight without carrying human bodies. Later settlements may create new branches of human experience. The inability to promise return does not make departure irrational. It makes the choice deeper than travel. It also changes the responsibility of anyone who sends people across the gap. A mission advertised as exploration must not hide the possibility that it is migration. A promise of arrival must include stopping. A promise of survival must include repair. A promise of return must account for both the spacecraft's trajectory and the time waiting on Earth. The first image can now be seen again. The spacecraft has reached Alpha Centauri. Ahead lies another star. Behind it, the Sun is a faint point among countless lights. Navigation can identify that point. A computer can draw a line toward it. The laws of physics do not forbid the ship from following that line. But the point marks more than the position of the solar system. It marks the place where the journey began, the people who shared its beginning, and the time in which departure still had a return waiting inside it. Coordinates may always show the travelers where Earth is. They cannot show them the way back to when it was home.